Hello everyone. This video will be covering week 3, chapter 3 materials. And before we get started with the chapter 3, I want to quickly go over some of the key terms that we went over for chapter 1 and 2. Chapter 1, we talked about introduction to research, statistics, and study designs. So we talked about how population is original target that we are interested in finding the laws of nature or truth about. And since we cannot possibly test everyone in the population, we take a subset of that, representative of the population, and we call that sample. And individuals who participate within sample, we can call them participants. And whatever we find from the sample, we try to infer back to the population, infer, meaning we want to determine whether what we found in the sample, whether it's a pattern of behavior or a certain trend, can that be generalized back to the original population that we are interested in. And in order for us to do that process, we have to collect data. And when we're collecting data, they are usually for the data are the scores from the variables that we're interested in. And there are two types of variables, quantitative or qualitative. Quantitative has a quantity, it has an amount in numbers, whereas qualitative, it has a quality. It only has categories, and it does not have an amount or it cannot be described in numbers. And there are two types of statistics. Again, statistics is a tool that psychologists use to conduct research, to understand what's going on within their research. And two types of statistics include descriptive and inferential. Descriptive statistics help us describe and make sense of our sample data to organize and summarize what we see. Once we do that, we use inferential statistics to make an inference, to use the sample data and generalize to the population. We call that inferential statistics. And in study design, the design could either be experimental or correlational. One way to make it differentiate between the two is to see if the researchers are manipulating anything in the design. If the researcher is manipulating a certain variable, that's an independent variable with a certain number of conditions, and that is an experimental design. But if researchers are not manipulating anything, that is correlational, because researchers are simply measuring via surveys or questionnaires. And then scores have mathematical characteristics, and we have to determine the scores, the data that you collect, have what types of mathematical characteristics to determine the specific types of statistics we can use. So first characteristic is measurement scale. You have to determine whether your scores are either nominal, ordinal, interval, or ratio. It is automatically ratio when 0 makes sense, 0 as an absence of that characteristic. Or the variable, the scores could either be discrete or continuous. Continuous, as the word says, the scores don't end. It just continues, meaning the decimals make sense. So if the score can be 1.1, 1.2, and 1.3, and the number just continues, that's a continuous variable like weight or height. Discrete variable means there are gaps. Only whole numbers make sense, and decimals cannot happen. So either you have 1 pet, 2 pets, 3 pets, you cannot have 3.5 pets, so that's a discrete variable, number of pets you have. And then we talked about how in chapter 2 we covered frequency, and we talked about how raw scores can be organized into frequency, specifically in frequency table and graph. And again, depending on what type of variable you have, the scores, what type of mathematical characteristics your scores have, that changes the type of graph you make, whether you're making a bar graph or histogram or even a polygon. And once you have a graph, you can determine the distribution of that frequency of the shape. So if it's normal, you see the one peak in the center, and that's the highest point. By highest point, we mean the highest frequency. As frequency, it's occurring most frequently. positively skewed as peak tilted towards left, negatively skewed on the other side, and bimodal has two humps like this. Okay. And then finally, we talked about the relative position of your score, or of your raw score, compared to the rest of the scores with the concept called relative frequency, percentile, and cumulative frequency. Relative frequency formula is frequency divided by n to get relative frequency. Both percentile and cumulative frequency talk about all the numbers that are at that score or below that scores, but percentile is in percentage, whereas cumulative frequency is all the frequencies added up, so it's in whole numbers. Okay. So if you I'm going over this really quick because it's all the content that I went through in the 2 previous videos. So if you're unsure of any of this term, or I talked too quickly and you didn't quite catch it, make sure to review the videos, the lecture notes and slides, so that you can make sure that you understand everything in here. Those are the foundations that we're going to build upon for the rest of the semester. All right. So in chapter 3, we're going to talk about one way to summarize scores, specifically with measures of central tendency. So in statistics, whenever we use X, we're talking about a score, raw score that we collected from our participant in our sample. So remember, we learned the term statistic. Oops. Excuse my terrible handwriting. And parameter. Statistic is for sample statistic. Parameter was for population. Whenever we use English letters like this, we're talking about statistics, which means it's for sample. Whenever we see a Greek letter used, that's for parameter describing population. So X, this raw score is from our sample, so we call X. This summation sign you saw from your homework 1, that's summation sign, okay? So if you see sigma and X, that means add everything that's X. So if I tell you X is 5, 4, 5, 6, and then I told you to sum all the X, you would just simply add all of these X's, and that would be your sum of X, adding all the scores together. So central tendency is one type of descriptive statistics. I briefly mentioned above in the review that descriptive statistics help us summarize and organize our raw data. Okay. For example, with the example results in the exams, I cannot really tell what's going on as a class as a whole if I'm looking at individual scores or even just frequencies, right? So instead, it's useful to shrink all the data, whether you have 20 people's data, 200 people's data, or 2,000 people's data, into just one summary score, so that by just looking at one number, you can gauge what's going on in that particular sample. So for example, you take an exam, and I know student A got 70, student B got 75, student C got 85, and so on. So instead of looking at those individual scores, if I know, okay, class average was 75, then I know in that one score that, oh, everyone on average was getting C or above. That's good. So that's the functionality of using central tendency. Okay. So central tendency tell us which scores in distribution are generally high or generally low. Because it describes the sample as a whole, you just use one number to describe the entire data. That number becomes the comparison point. We can compare rest of the scores to that score, that summary score, to see, okay, did I score generally high or low? Another way to describe that is if a variable is a continuum. The variable, like exam scores, is a continuum. It continues from score 0 all the way to 100. then a score is one specific location within that continuum, okay? And difference between the two scores in the essence is the distance between two locations. So if I have everyone scores on exam from 0 to 100, okay, and let's say student A scored right here, student B was here, and student C was here in their exam scores, the difference between these two people's scores is essentially the distance in this continuum, okay? So basically just making all the variable as a horizontal distance line. Okay, and measure of a central tendency tells us, okay, if we summarize these three people's scores in this continuum into just one location, that is the function of central tendency. Tells us in general where these people's scores lie in this continuum of the variable. And we're going to be covering three types of central tendency: mean, median, and mode. And I'm sure this is going to be a quick review of the concepts that you've already learned or you're already familiar with. The first thing is mode. Mode is the score that has the highest frequency in the data. So it's most frequently occurring score. So let's say this is set of your set of raw data that you collected. So this person got 2, another person got 2, this person got 4, and so on. And then you look for a particular score that is most frequently occurring. Most people had this score. And judging by this data, looks like it's either 2 or 4. It looks like it's 4 because we have 1, 2, 3, 4, 5, 6, 7, 7 fours. Okay, so 4 would be our mode. There is no mathematical or statistical symbol for mode. You just call mode mode, and it's it's always used for nominal scale. Remember, nominal scale is when there are names, categories instead of numbers, like hair color, what else? Race, gender, those kind of categories that are not numbers, you report mode. Remember, mode is the highest frequency. Highest frequency in graph means highest point. Remember, in frequency distribution graph, this is all your scores, x, and y-axis is the frequency. So highest point in the graph means highest frequency. It's most frequently occurring. So if when the polygon, this polygon is a type of graph, right, has one mode, one highest point, one score that has the highest frequency, we call that unimodal. So there is only one unimode. When the polygon has two peaks, so there are two highest points that has the highest frequency, then we call that bimodal. There are two modes. So when we talked about the shape of distribution, whether it's normally distributed, positively or negatively skewed, or bimodal, that's where this comes from. That means there are two modes, means there are 2 points that have the highest frequency. But mode is far from perfect. Just by picking a number that has the highest frequency is not very useful, especially when there are multiple scores that have the same highest frequency. So in this example, you see 2 and 3 and 4 all have the same number of frequencies of 6, right? So 2 has frequency of 6, 3 has frequency of 6, and 4 has frequency of 6 too. What to do? In that case, mode is actually both 2, 3, and 4. So then mode is not really useful because the mode is all the data, okay? And also, mode ignores all the scores that are not actually most frequent. So what if we're missing out the important piece of data? Looking at this example, looks like there are 6 people who scored 2, but the rest of the 12 people scored quite differently from 2, okay? So if you summarize this entire data set by just saying, okay, mode was 2, so in general, looks like everyone scored 2, that's a wrong piece of information, because actually majority of people scored scores that are far from 2. But just because 2 was most frequently occurring score, it wrongfully summarizes the entire data set. So mode is not perfect. The second type of central tendency is median. Median is a score at the 50th percentile. Remember, we learned percentile in chapter 2. Percentile is the percentage of all the scores at and below that particular score. In other words, the median, at median, there are 50% of people scores who are lower than median and 50% of the scores that are above the median. That's what that means about median being the 50th percentile. So half the scores are above and half the scores are below this median score, whatever that is. And median is used for scores that are ordinal. Remember, ordinal is the scores that have ranks, but not necessarily have equal distance from one another. Or even if when you have interval or ratio data, if they are highly skewed, so either positively or negatively skewed, you have to report median. And we'll discuss why that's the case in a second. Symbol for median looks like this. The easiest way to find median if you don't have that much data is to line up your data from the lowest to highest and find the middle point. So looks like the middle point is 4, and 4 is your median. So at this point, half of the scores are below this score and half the scores are at and or above this score. So there are 50% here, 50% here. So this median is at the 50th percentile. But what if there are 2 scores? So let's say in this example, instead of ending at 6, there is another 6 here. Now there are even number of raw scores. Now if I were to find center, there are 2 scores that are in the middle. When that happens, you take the average between the 2 scores, and that's your median. In this case, our 2 middle scores happen to be the same, so the average would be just 4. So a median is an improvement from mode because it only had each distribution, each set of raw data can only have one median. So you won't run into the same problem that you saw with mode when you have multiple highest frequency scores. Okay. And median score tends to be where most of the scores truly are located because it's also at the 50th percentile. But the problem is, just by looking at the geographically middle point of the distribution is not the most precise way of summarizing the data point. Okay. And if your data are interval and ratio that have perfect normal distribution, then median and mode are the same. So again, it's not the most useful piece of information. And finally, median again reflects more of the frequency, how many times this particular score is occurring, rather than true mathematical value in summarizing the data set. So that's when we move on to the mean. Mean is located at the mathematical center of the distribution. You know it as average. We've all heard of average quite a bit at this point, right? So while median was the physical, geographical center of the scores, remember we lined all the scores up and then we found the actual middle point. Mean is moving beyond that physical geographical location. It's actual mathematical center. Okay. And mean is most commonly used in central tendency, as you've experienced yourself. And when you have normally distributed interval or ratio data, you always report mean. And remember, mean is a mathematical center. It means that mean has a mathematical formula. I don't know why this symbol looks like this, but this S is actually supposed to be sigma, okay? So sigma x divided by n. Do you remember that we learned sigma x in the on the top, and it was also your homework question? You sum all the raw scores in your data set, you divide that by the total number of participants, and that's your mean. So statistical symbol for mean, it has a hat, bar, and then X. That means it's average, okay? And by summing up all the raw scores, that means it does not ignore any information in your raw data. Remember, mode is just looking at the score that is highest frequently occurring, and median is also the number that is in the middle of the scores. So all the scores that's not frequently occurring or that's not in the middle get ignored in mode or median. But in mean, because in mathematical way, all the scores are added up, all the scores are part of the information in calculating this central tendency. Okay, so it gives us the most information about the data because no scores are ignored. Okay, again, to write it neatly, average is sum of all the raw scores divided by n. So because the mean is the mathematical center of the normal distribution, it does give us an accurate location in summarizing the data in the distribution. But mean is not so accurate when you have skewed distribution. So this is an example. When you have normal distribution like this, when you have one peak, one highest point, that means the highest point of any distribution graph is always mode because it's the highest frequently occurring number. And in normal distribution, it's symmetrical in the middle. So this point is 50%, and this half is 50%. So it's this middle point is also median because it's at 50th percentile. And it also happens to be the mean too. So when your data are normally distributed, your mean, median, mode are all the same. Of course, in real data, the data might not be always perfect. So the mean, median, mode might not be exactly the same number, like 15.5. But as long as they're around the same range of the scores, they're really close to each other, then you know, even without looking at the graph and looking at this distribution, you know that the shape is normally distributed because mean, median, mode are all around the same number. But if you have skewed distribution, whether it's negatively or positively skewed, mean, median, mode gets scattered out throughout the distribution. Mode is always the easiest to find because it's the highest point of the graph. So whether it's normally distributed or skewed, the mode is always the highest point of the graph because that's the highest frequency. On the other hand, mean is always towards the tail, whether it's negatively or positively skewed, because remember, mean, add up all these scores when you're calculating the mean, sum of x. So all of these scores are included in calculating the mean. So all the scores that are not so frequently occurring, but they still exist, all these scores drag mean towards them. The mean gets dragged towards the tail. So in the skewed distribution, mean is always towards the tail, towards the tail. And finally, median, again, is the middle point. So it's somewhere in between mode and mean to make sure that they are taking up 50% below that point and 50% above that point. And that usually falls between mode and the mean. Okay. So let's start over. So in other words, if you find mean, median, mode to be all the same, then you automatically know it's normal distributed. But if you find these three central tendency scores and find out the mean is much lower, much smaller than the mode, and median is in the middle, then again, without looking at the graph, you know that the shape is negatively skewed. That's when mean is the lowest score, median second, and mode is the highest score. However, if the graph is positively skewed, mean is the highest score and mode is the lowest score between the two, and the median falls in the middle. So by comparing the sizes of these three central tendency scores, you can automatically determine the shape of the distribution. This will definitely be on your quiz, review question, and exam. So make sure you know how to compare and contrast the central tendencies to determine the size of the distribution. Okay, again, this is a summary of the comparing mean, median, mode. You use different types of central tendency depending on the type of data or skewed distribution shape you have. All right, so if we were to practice, let's say I asked you how many number of minutes you meditate per day, and 18 participants gave me their score. So this person meditated 14 minutes, this person meditated 13 minutes, and this person meditate 14 minutes, and so on. So there are n of 18. And now I want to summarize this data so I can effectively communicate and know what's going on in this entire data set. To find a mode, it's the most frequently occurring score. So we organize the raw score that we had above into the distribution table. Remember, the first row is the score, and the second column, is the frequency. And you organize the scores from the highest to the lowest. And by looking at this frequency number, you can quickly determine, okay, so 6 is the highest frequency number, which is 14. So 14 has the highest frequency, so our mode is 14. So most people are meditating 14 minutes per day. Median, again, is at the 50th percentile. So if we were to organize all of the scores, line them up from the smallest, or 10, 13, to the highest, we find the middle score in between. And it looks like in this case, 14 and 14 were in the middle. Again, like I said, if there are two scores that are in the middle, you take the average between the two. And in this case, because they're the same number, the average is again 14. And 14 is the median. So 14 was also mode and median. And finally, we need to find average, mean. Again, I don't know, the symbol went wrong, but this is sigma sign, and this is also sigma sign. So remember, on the raw data, these are all your x's, and you add all of them up. That's your sum of x, 246, and there were 18 participants, so you divide that by 18, so your mean becomes 13.67. Okay, so it looks like mode was 14, that has the highest frequency. Median was also 14 because it was right in the middle. And finally, mean is 13.67. So even if we didn't graph this raw data, just by comparing these three central tendency scores, we know that they're all pretty much the same number, meaning that it's normal distribution. Again, normal distribution has mean, median, mode all falling in the same line right in the middle because it's the highest points. It's mathematical and physical center of the distribution. So our data above was normally distributed. How about here? So this distribution is positively skewed. our tail is tapering off towards the right, on the positive side. The first thing you do is finding the mode. This highest point is the mode. And I said mean always gets dragged towards the tail. So this one closer to the tail is mean. And the one in between mode and mean has to be median. So again, let's say mode was 12, median was 13, and mean was 14. If the mean is higher than the mode and median falls in between, then we know just by looking at these three numbers that the distribution is positively skewed. But this one, again, mode is always the easiest to find because it's the highest point. So this is your mode. And mean gets dragged towards the tail. So this is mean. And finally, the one in the middle has to be median. Okay, so let's say mean was 7, median was 9, and mode was 11. So whenever mean is the smallest number out of the median and mode, then we know the distribution shape is negatively skewed. All right, the textbook also has this diagram. So like I said, make sure you can determine the shape of distribution by comparing these three scores and vice versa. When we apply the mean to research, we have to learn the concept of deviation around the mean. By deviation, I mean distance. So in normal distribution, we know center is the mean, and we usually compare everyone else's score to the mean, right? So I only know my raw exam score is relatively good or not once I know the class average, right? So I think in the earlier video, I said, if I scored 70 in my exam score, my 70 is not so bad when the class average is, let's say, 50. When class average is 50, I know a lot of people scored around 50. So my 70 compared to that class average of 50 is very, very good. My 70 is far from that average. But if class average, let's say, is 88, now my raw score 70 is lower than the class average of 88. Okay, so by looking at distance from the mean in what direction, I can see where I stand compared to the rest of the people in the class. So by deviation around the mean, we mean that we're calculating the distance of each person's score from the mean. So how much your score differs from the mean is its deviation distance. And you calculate that by having that raw score subtract the average, mean. Okay, so if you have a score of 6 when you know the mean is 5, it's 6 minus 5, so your deviation score is 1. When you have score of 3 minus average is -2, and your deviation score is negative. So in this calculation, the number itself determines the distance from the mean. So higher number means it's farther away from the mean. Just like when we know by when we're measuring feet or yards. Okay? And sign indicates the direction from the mean. For this, there's positive sign, meaning my score is higher than the mean. And it was, right? 6 is higher than the average 5. The negative sign, on the other hand, tells me that the raw score was smaller than the average, and thus the negative sign. Okay, so just by looking at the deviation scores, you can also determine the raw scores and where they are relative to the mean. If the number is high, we know it's farther away from the mean. If the number is small, it's close to the mean. If it has positive sign, it was bigger than the mean. If it has negative sign, it's smaller than the mean. And one mathematical fact about the deviation around the mean. If you add up all the distance scores of all the raw score, you calculate the distance from the mean for each raw score, and you sum them all up, sum all of the distance scores, that always adds up to 0. Why? Because normal distribution is symmetrical. So if you calculate the distance of each raw score on both sides, they get canceled out. So it becomes 0. So just like this, let's say I have raw score of 3 and raw score of 5. The deviation score for 3 is 3 minus 4 if the average is 4, and deviation score is -1. Again, negative sign tells us the raw score was on the left side of the of the average. It was smaller. If your raw score is 5, your deviation score is 5 minus 4. So again, 1. This one has positive sign because the raw score of 5 is not smaller than the average. It's bigger. And of course, if you add these two up, it cancels out and it becomes 0. So if you add up and if you do the process for all these infinite numbers, they cancel each other out. So if you add up all the deviation scores, all the distance from each of the raw scores, it always adds up to 0. And finally, the population mean. Again, remember when we were looking at the sample mean, we wrote it like this with English alphabet, meaning it's sample, statistic, we're describing sample score. When we're describing population, we use Greek letter mu. We call it mu. And if you were to collect all the raw scores from the entire population, you add them all up, and you divide by the entire population, you would get the population mean. And population mean has the same mathematical characteristics, such as if you sum all the deviations around the population mean, it also adds up to 0. If our sample is a true representation of the population, then our sample mean should almost equal to the population mean. All right, that's all I have for chapter 3, and I'll see you at the chapter 4 lecture.